Now we will start our technical session. So, uh, in this part of the technical session, our first presenter is Mahendra Kumar Gohil. He is from IIT Kanpur. Today, his topic is uh, design, kinematic, and control of four-wheel independent steering and four-wheel independent driving robot for agriculture automation. Over to you, Mahendra.
Good afternoon, everyone. My name is Mahendra Kumar Gohil. I am currently a research scholar in SMSS Lab, IIT Kanpur. So today I am going to present my topic, design, kinematics, and control of independent steerable mobile robot for agriculture automation. So before starting that, I will start with the challenges of this kind of agriculture robot. Uh, if you see rough terrain navigation is a difficult task. Why it is difficult? Because when you move in the specifically for the agriculture scenario, when you move the robot in agriculture field, you will find that different crops have different height and planting distances. Uh, at the same time, when we do the irrigation in the field and when we do the irrigation in the field, it becomes wet and slippery. At that time, it becomes more challenging to drive the robot in that field. After the crop has matured, and so there is a no clear cut path visibility in the field. At the same time, because of different crops height, we have to adjust the a particular kind of robot cannot do all the tasks in different kind of crop height and field environment. So why we started to work on our agriculture robot? So as you know that sustainable agriculture is key to robust economic growth. Precision agriculture and data-driven approaches help in increase in agriculture productivity by increasing crop output, reducing losses and cost of inputs. One of the significant factor in increasing the productivity is identification of crop diseases, field management, and taking preventive steps to eliminate them and avoid further disease spread. Flexible modular platform that enables automation of tedious farm related activities are essential to boost agriculture productivity. As you all know that agriculture and farming, it is a very tedious task, and with growing number of population and narrowing of the agriculture land, it will require precision agriculture and data-driven approaches for agriculture productivity in yield increase. So key objective of my today's talk: autonomous robot with inbuilt navigation module for rough farm terrains. So this is the basic objective of our project. Precision pesticide delivery, harvesting and seed sowing, and multiple agriculture field activities mechanism. So we are not targeting, means we are wanted to make our platform robust as possible. So in which we can include as many things. Means one of the main thing was the precise pesticide delivery system for our robot. Second part is after this means the plant has matured, we want to do harvesting. At the same time, at the initial stage of the plantation, we wanted to make seed sowing and seed sowing with our agriculture robot. And multiple agriculture field activities means based on requirement, we can include the multiple things in our agriculture robot. Means it should be modular. Efficient data acquisition system. So means at the same time, we also wanted to collect that on the field testing system. We wanted to create the on the field testing system. So means our robot can take the soil sample from the field and do the on field analysis. And flexible platform supporting continuous upgradation. Means that I have already explained. So what is the current agriculture state of the art? So right now there is a lot of interest of around the world for the agriculture robot and agriculture automation. So many part of the world, people have developed a different kind of robot, and they have different targets. So I will just show you the list is quite vast. I will show you the most of the three which are at the current at their top. So one is this Thorwald agriculture robot. Yeah, it has been developed by Saga Robotics, and this is a swag board, and this is a Ladybird, and these are from the University of Sydney. So we took inspiration from them, but we also found out that there are many things which need upgradation, means from our current Indian scenario also, and for the requirement of the farm field also. So means we found that like this Thorwald agriculture robot means it can work on for the smaller crop plants, but when we go for the plants which are bigger in height, then you need a lot of adjustment to modification for this kind of robotic system. This swag board was especially designed for the not the crop, but for the uh, any farm animals management. So but they are using it for the farm also, but it was mainly designed for farm animal management. And this Ladybird, they incorporated the solar panel in the system, but it's also because of these things to make it without installation of solar power panels made it autonomous for long time and without any power recharging. But at the same time, it has reduced the capability of the system, means it has made it very less modular. So based on seeing those things, we developed our own design. So this was our initial version 1 design, which I have shown you. We are also working on we have worked on version 2 design of the system. So this is our design is a flexible nature. So based on the crop requirement, we can adjust the height of the robot as well as the wheelbase of the robot. And we also have the system on the chassis that we can fit the robotic arm and different kind of systems. So this is the typical arrangement of our robot. Adjustable robotic arm configuration is there, and this is our suspension system, and this is our steering system. And flexible robot manipulator means we can adjust the height of the robot, and this is the robotic arm which we can fit in the system. So I will now. So this means it has total 8 degrees of freedom. So 4 degrees of freedom comes from these 4 wheels, and this 4 degree of freedom comes from the 4 steering mechanism. Because in the field where the space is limited, you need to think about lot of things. You cannot make the robotic system like a car kind of system, because a car takes a larger turning radius, and in the field if you do this kind of thing, it can damage the crop. So we have to increase the total degree of freedom of the robot to cater those things. So and our robot is reconfigurable, means in chassis width and height can be adjusted. So I will go in the brief kinematic description of our robot. So this is the kinematic model of our robot. As you can see, there are 4 independent wheels with 4 independent steering system. So this B and this A, if you can see, we can adjust the width of the robot as well as this length of the robot also. And at the same time, we can increase the height of the robot. You cannot see because it is the top view of the robot. So this all the 4 wheels can be controlled independently. So these are basic joint parameters which I have described. I have described to W1, W2, W3, W4, and delta 1, delta 2, delta 3, delta 4 are the steering angle of the individual wheels. And the same time psi total orientation of the robot is represented by theta, and velocity of the robot is represented by Vx and Vy, and individual wheel orientation is represented by delta 1, and independent wheel velocities are represented by Vx1, Vy1. So so in this way so this is the location of all the 4 wheels respect to center means wheel robot coordinate frame. and this represent the V represent the velocity of the robot, and VI represent the velocity of each individual wheel. Uh, to simplify those things, omega is denotes the angular velocity of robot, and omega denotes the steering velocity of each individual wheel. We have made some simplification for our to do the kinematic analysis of the robot. One simplification is that the position of the center of mass and the centroid of the robot are the same. Both radius and mass of the wheels are assumed to be same. Under no slipping condition, relationship between velocity, wheel velocity and robot velocity is obtained by rigid body constraint equation, and it is given by means velocity of each individual wheel in x direction can be represented by velocity of robot Vx minus omega and by omega I. Similarly, for the velocity of each individual wheel in y direction can be represented by this equation. So these are the basic state variable and Lagrange formulation for our robot. So state variables are basically total 11 state variables are there. Robot position we will be represented by x, y, theta in world coordinate frame. Wheel rotation angle psi 1, psi 2, psi 3, psi 4 will represent the wheel rotation angle, and delta 1, delta 2, delta 3, delta 4 will be wheel steering angle. So this is the state variable, and in this way q dot we can represent through with this Jacobian matrix and with respect to each individual wheel velocity and steering angular velocity. So now the kinetic energy of the system can be represented by Ex, Ey, E theta, E psi and E delta, means which means kinetic energy in x direction, y direction. I theta will represent the means wheel due to rotation of the system, what will be the kinetic energy, and this will be represent the kinetic energy of each individual wheel. By this way, we have derived the kinematic and dynamic model of the robot, and this is the kinematic state variable, and this is the representation of the robot in the dynamic environment. Now, currently we are working on the control system development of the robot. So for the testing purpose, we have started with the feed forward control. Feed forward control is an open loop control in which we give the input, but we don't measure the output. So there is a no error measurement, but this is very good thing to do if you are wanted to do basic level of testing of the environment. We want to capture the basic nature of the robot, then you can start with the feed forward control. And feedback control is means it will be basically used for the trajectory control of the robot. So means suppose I want to move the robot in the desired trajectory, and so we need a continuous feedback signal of error that my robot is following that path or not. For that we need to do feedback control. So we have currently tested the robot with feed forward control. We are working on the feedback control because there are some many non-linearities in the state space model. So we are working with the best model. So three approaches we are planning to work with. One is the linearized control scheme, sliding mode control, and model predictive control. So this will be the typical control mechanism of our robot. So it will start with the kinematic control, and after that there will be dynamic control of the robot. So because dynamic control will give us the more robust control system for our robot, and kinematic control will be useful for the initial trajectory and it will give us the basic kinematic nature of the robot. So we started with this basic simulation in feed forward manner. So we means it's a 2D simulation, and we started with the MATLAB, and we have generated the basic trajectory. Means this is a trajectory the robot should follow in the field, because in the field, if you will see, it will come in the later stage. It should run in a zigzag manner in the field. So we have started with the basic simulation in the MATLAB. So in this way, a robot will cover the entire field in this zigzag manner. Now, because this to simulate simulate the actual condition, we have developed a model of our field in the Coppelia Sim, which is a physics engine in which we can develop the deploy your actual model and test the in actual scenarios. So, so we have created our agriculture field here, and this you can see as a crops crops arrangement in this field. And we have tested our robot, and there we have, you can see that one camera is there, and which we can see that what robot is actually seeing. So we have started testing algorithms on this simulation environment. It will be basically control algorithm as well as different type of mechanism which we for pesticide and all this testing will do in this simulation environment. Now I will show you the real field which we are planning to work. Means we have started working in this field. So this is our actual agriculture field. So we have planted the potato crops here, and we have tested. And this is the at the starting stage of the field, and this is the after the during the harvesting season. As you can see that the after the maturity period, the field becomes quite occupied with this potato plants, and so it is challenging task to navigate in the field. So because there is no clear-cut distinction as compared to initial field, clear-cut distinction of different rows and that one. We have also tested our robot. We have tested the pesticide delivery system of our robot in the field. So this is a basic test of our robot, which we have started to. So we have successfully tested our robot. So it proved the proof of concept. Now we are working on the control part of that. Thank you. If you have any question, you can ask me.
Thank you, Mahendra, for your nice presentation. So I request if audience have any questions, kindly you can ask. Okay, I have a few questions. First one is like, you have used 8 actuator, all right? Can you go to that slide where you showed the 3D model?
Yes, yes.
Okay, how you have controlled the height of the robot?
Okay, height of the robot. As you can see here, this flexible shoulder is there. So in this this mechanism, we can rotate this arm, and we the height of the robot.
So it's a kind of, there is a lock, and you manually rotate the link.
So we, in there, as you can see the shoulder here, we can lessen the screw there, and we rotate this this 4-bar mechanism here, and it will we will adjust the height, and we'll lock there. So it will, this way we'll adjust the height of the robot.
Okay. And second question is, you have four motors in 4 wheels, right?
Yes, yes.
You have 4 motors in 4 wheels, and moreover, you have four actuators in 4 rotating axis of the wheels, right?
Yes, yes, yes.
So, like I think if two of the wheels, if you replace with caster wheels, so like it may reduce the number of actuator, or it will affect some.
Okay, so you are saying, or we can use two caster wheels. It will
Yes.
use the number. Okay. So what we found now that while initial testing also, so because if you are using the caster wheels, so suppose my robot is going in the front direction, and suppose I have to move in 90-degree angle. Okay. So in this arrangement, I just have to steer the angle of this steering system, and it will the just 90-degree direction. Okay. With the caster wheels, suppose only I'm using two caster wheels and two driving wheels, then there will be some kind of a turning radius. So in the agriculture field, this kind of spaces are very less. So in many area we cannot go. So we need some kind of
Okay.
that's why we not use the caster wheels.
Okay, I mean, if you replace the diagonal wheels, not like okay. In the wheels which are in diagonals, two wheels you can keep in passive, and the two wheels which are in other diagonal, if you put active, then I think you can achieve 90-degree rotation with caster wheels.
So you are saying these two wheels we can use as a diagonal wheels as a caster
wheels? Yes.
Okay. Yeah.
Just suggestion that
may think that how anyway actually while testing we will generate different kind of scenario. In initial testing only we tested with this two wheels only, and two we kept as a passive wheels. So means because in many field time actual field testing situation might arise that in two wheels there is a no power cut or some power issue, then robot should work without with two wheels also. So we are actually generating different kind of scenarios. So we will be definitely make them as a passive wheel, and we will test that.
Okay. Thank you for your reply.
Thank you, Nayan, for the suggestion.
Hi, Nayan. Just to add one point here, that this particular four-wheel drive is always preferable in a situation where more traction or improved traction is required. As Mahendra has pointed out that during irrigation the field is kind of wet, and the slipping is more prominent there. So in that case, if we use the caster wheels, there are high chances that we may not be able to steer or control the robot in a very desirable fashion. So four-wheel drive is always preferable in case.
Of course. Yeah, I understand. Okay, thank you.
Thank you, Kanaya, for the point. I also missed those points. Thank you.